So in this session we are going to discuss the thermal expansion of solid and fluids and related concepts we will discuss. First one is for solids. For solid undergo three type of thermal expansion. One is one dimensional and another one is 2D and third one is three dimensional expansion. The one dimensional is called linear and this is called areal or superficial, and this is volume expansion. Yes, what this says, fractional change in length is directly proportional to change in temperature. Fractional change in area where is directly proportional to temperature. Similarly, fractional change in volume is directly proportional to change in temperature, where this delta is generally called L final minus L initial. Similarly, this has to be A final minus A initial. Yes, similarly, this has to be final volume minus initial volume. So I can remove this proportionality is by using some constants. So here I can write that, so delta L by L initial, that is equal to alpha into delta theta. This is called the coefficient of linear expansion. Coefficient of linear expansion. So similarly, we can name it here also the delta A. Yes, delta A by A initial, that is equal to beta into delta theta. And similarly, here I can write delta V is delta V divided by V initial, that is equal to gamma into delta theta. How we call it as alpha as coefficient of linear expansion. This is coefficient of areal or superficial expansion. This is coefficient of volume expansion. And there is a relation between these three variables or that proportionality constant. That is beta is 2 times of alpha and gamma is 3 times of alpha. And the ratio of alpha, beta and gamma, that is equal to 1:2:3. And moreover, yes, you just see that whenever there is a thermal change in temperature, either length or area or volume of the substance can change. So therefore, for example, density at some temperature is generally density is mass by volume. Now say that is some temperature for theta initial. Now, when the temperature changes from theta initial to some other value theta final, the corresponding change in density can be written as m by v dash. Here you see that mass of the substance will not be affected by the temperature change. So I can write this expression. So rho dash, that is equal to m divided by v dash. You just expand this equation, we can get that v final is equal to v initial into 1 plus gamma into delta theta. Similarly, area final, that is equal to A initial into 1 plus beta into delta theta. And similarly, here also I can write that L final, that is equal to L initial 1 plus alpha into delta theta. Okay. So by using this expression, this V dash or V final, you can take any notation, no problem. So I can write that is V initial into 1 plus gamma into delta theta. But this mass by initial volume is nothing but initial density. Therefore, I can write that as rho final or rho dash. You can use any notation, that is equal to rho initial divided by 1 plus gamma into delta theta. Or if you are taking this one to the numerator and by using binomial expansion, we can write that rho initial into 1 minus gamma into delta theta. So these are some important results to explain this concept. Now I am going to discuss about expansion of liquids, thermal expansion for liquids. Yes, now you see that for liquid it undergoes volume expansion. Yes, when compared to its areal and linear expansion, volume expansion is more dominant. Therefore, for fluids or for liquids, I can write that The first one is the change in volume. It's mostly the dominant change or expansion is three-dimensional volume expansion only. Therefore, V final that is equal to V initial into 1 plus gamma into delta theta. This is coefficient of volume expansion. Yes, whenever this change is there, the corresponding density. So this may be rho initial. You can write rho naught or rho initial divided by, as we written here, is 1 plus gamma into delta theta, or by using 1 plus x power minus 1 binomial expansion, we can get that as rho initial 1 minus gamma into delta theta. So these two relations are important in the case of liquid. Yes. And this next one is related to this concept. We will discuss about apparent change in volume, or delta V apparent. So apparent change in volume. Let us consider whenever a container is heated. So you just consider there is some vessel. So whose volume expansion is given as to be gamma solid, and inside some liquid has taken, whose volume expansion is taken as to be gamma liquid, and this is for gamma solid container. Okay, let us consider initially at theta initial temperature, both the volumes are considered as to be equal. That means the volume of the solid container and the volume of the liquid is the same. Now the temperature, when the temperature is, say for example, theta initial, and when the temperature changes, and what will happen means simultaneously the container will expand as well as the liquid also gets expand. So therefore, and you just see that. So this is the expansion in a container when compared to its normal position. And meanwhile, this is the initial level of the liquid. Yes, when compared to that, the liquid also may increase in its volume. Yes. So this is the change in volume of the solid container as well as the liquid taken in this. Therefore, I can write that for a solid container, yes, we can say that the corresponding volume is V solid, that is equal to initial volume. Since initial volume is same here, so V solid is equal to V liquid initially. So initial is value, say for example V naught or V naught liquid, like that. Therefore, we can say that is V naught into 1 plus gamma solid delta theta. So in the case of liquid, for liquid we can write that. So for liquid we can write that the same expression V liquid. So the initial volume of the liquid and solid containers are assumed as to be equal. Therefore, V naught into 1 plus gamma liquid into delta theta. Yes. Now you please see that. Yes, what is the apparent change in volume is nothing but the apparent change delta V apparent volume expansion of the system, that is given by volume of the liquid. So V liquid minus V solid. So that means just to subtract these two equations, what you will get means V into the initial volume, say that is value has to be some V naught, the initial volume is V naught. Therefore, I can write that V naught into gamma liquid minus gamma solid into delta theta. As we said here, gamma solid is 3 times of its linear expansion. Sometime here also we can use, instead of gamma solid, volume coefficient of volume expansion of the solid, we can use 3 times of its linear expansion also if you need. So from this expression we can say that the delta V may be positive or negative or 0, depends on this parameter. This term is called coefficient of apparent volume coefficient, apparent volume coefficient of thermal expansion. So now you see that I can categorize this as to be a 3 category. So we can write this as to be 3 cases. Now you see that if delta theta is fixed, and we can compare these two terms. If gamma liquid is greater than gamma solid, then if gamma liquid is greater than gamma solid, then delta V is positive. Therefore, delta V apparent will be positive, which means that the liquid level may be increases. So liquid level increases, liquid level is increases. But in the case of suppose both are having yes same value, so gamma liquid equal to yes gamma solid. In this case, this term delta V becomes to 0. Therefore, delta V becomes to 0. So therefore, no change in yes no change in yes level of the liquid, level of the liquid. Yes. Now please consider in this case, suppose gamma liquid is lesser than this one. So just opposite condition of this. So gamma liquid is lesser than is a gamma solid. In this case, delta V apparent will be negative. This means that there is a fall of liquid level. And this is the yes concept related to apparent volume expansion of the liquid. Now we will go to the yes another topic. When volume of the liquid changes, whenever a solid material is immersed in fluid, we discussed that we can say that the buoyancy force acts on the body generally. So the second concept, so buoyancy force, buoyancy force. So generally we know that, say for example for theta initial, for initial temperature theta, we can say that F buoyancy is equal to V solid rho liquid into G. For some other temperature theta final, temperature of the system may increase or decrease, but say that is some final temperature FB dash, that is equal to V dash is solid rho dash of liquid into G. So now you see that this expression, you just rewrite this expression V solid. Just now we wrote that V solid is nothing but V initial into 1 plus gamma solid into delta. So I can write this one as V initial into 1 plus gamma solid gamma solid into delta theta into the rho term. Rho we just now we wrote that the density, either this term, this is the approximation, but this is the actual expression. So this will be the actual expression without any binomial expansion. Therefore, I can write that has to be rho initial divided by 1 plus, since it is the density of the liquid we are talking about, we can write a liquid into delta theta into G will be there. So just see this expression, volume of the solid, initial volume of the solid and initial density and G. So initial volume of the solid, initial density of the liquid and G. This is F buoyancy. Therefore, FB into remaining term is 1 plus gamma solid delta theta divided by 1 plus gamma liquid into delta theta. So this is what FB dash. So this is the expression for a change in buoyancy force. Once the buoyancy force changes, the volume, the fractional volume inside of the solid material inside the liquid or fractional out, that and all will change with respect to this concept. Now you please go for the expansion of the gases. So thermal expansion of gases. In gases, both the pressure and volume, two parameter will change. So therefore we can write that so at any temperature we can write that here, that is P final, pressure P final, that is equal to P initial into 1 plus gamma P, that is volume expansion during the pressure change into delta theta. And similarly for volume expansion, V final, that is equal to V initial into 1 plus gamma volume into delta theta. So this is the expansion of the gases. So so next we are going to discuss that applications of thermal expansion. There are some MCQ problems are there related to this concept. The first application or concept which depends on the temperature change or its dimension change. The first one is called expansion of cavity. So expansion of cavity. Now you see that cavity means there is no material present. So let us consider there is a square plate of length, say for example L initial. It has a small cavity. Cavity means there is no material. So this is the solid material and this is the cavity of yes, radius A, for example R, or R initial radius. When this yes, square plate is heated, even though there is no material in the cavity also will expand similar to a circular disc of radius R initial. So therefore, when temperature increases, what will happen means, yes, the size of the square plate also will increases. At the same time, the size of the yes, cavity also will increases. So this is R final. That means this cavity expansion is very similar to expansion of a circular disc of radius R initial to R final. So kindly note down the theory, students. So now the second application of the thermal expansion, the second one is bimetallic strip. Bimetallic strips. Okay. So let us consider there are two different rod of initial length is L. Say this is material 1 and this is material 2, whose coefficient of linear expansion is alpha 1 and this has to be alpha 2. Say for example alpha 1 is greater than alpha 2 here. So when this composite rod, bimetallic means composite, two composite or different materials. When these rods are gets heated, then what will happen means, the material whose alpha is greater will lies in the outer side, that is convex side of the bimetallic strip. Yes, so this is the thing, right? Now you see that. So this is alpha 1, that is material 1, and this is the material 2. Yes. So the material whose alpha is greater, always lies in the convex side, yes, convex side of the metallic strip. These arrangements are generally used in a thermostat like iron box or something else. Okay. And the third application is thermal stress and strain. Thermal strain and stress. This concept is already discussed in properties of solid, but anyway it's related to here. Once again I can explain here. Yes, we know that for any solid, the fractional change in its length is equal to alpha into delta theta. As per the definition of strain, the change in dimension to the original dimension, this is nothing but strain. So this is the thermal strain. Yes. So therefore I can write that the thermal strain of the given material is equal to alpha into delta theta. These strains can produce, let us assume that these are the two fixed rigid rods. Yes. So now you see that. So whose length is, initial length is L, and when it is heated, then what will happen? It is trying to push that away this rigid support, which develops some restoring force in it. So in this case, yes. So another one is this is thermal strain. So thermal is thermal strain. Next one is thermal stress. We know that Young's modulus Y is equal to is sigma thermal divided by this is stress by strain. Yes. So from this I can say that sigma Th that is equal to is thermal strain into Young's modulus. Thermal strain into Young's modulus. This is the another expression. And next we know that by definition we know that as sigma is equal to F by A. So from this I can write that force due to the thermal expansion is F is equal to sigma thermal, yes, that is the thermal stress into area. But the thermal stress is nothing but yes, thermal strain into Young's modulus. Therefore I can write that the force due to the thermal expansion is F is equal to, just substitute here. So therefore Ya into thermal strain. So this is the force due to the thermal expansion which acts on this rod, whether expanding or contraction takes place. But this is called a normal one, and in that case the second one what we said is called free expansion. Free expansion, yes, we are already discussed in properties of solid. Suppose a rod one end is fixed and another end is a free end. So when the rod is heated, its length will increase. So this is L and the change in length has to be delta L. But there is no restoring force developed in this case. So for free expansion case, we can say that S is 0, thermal strain is 0, as well as thermal stress also will be 0, since there is no restoring force developed. And the fourth application is fourth application. This is the third one, and next one is the fourth application, very important one. That is time period of a simple pendulum. Time period of simple pendulum. Simple is a pendulum. You know that what we know means generally time period of the pendulum is given by 2 pi root over L by G. Since this time period depends on length, whenever temperature changes, the length of the as a system will change. So because of that, say this is time period when temperature has a theta initial, the corresponding S length is taken as to be L initial. Now the temperature of the system is changed, either increase or decreases by theta final. Therefore T final is equal to 2 by root over L final is by G. But we know that formula L final is equal to L initial into 1 plus alpha into delta theta for one dimensional expansion. So in this case we can write that, so therefore just to substitute here we can write that 2 pi root over L initial by G into root of, since they are in product, I can write that this has to be 1 plus alpha delta theta, but this term is nothing but T initial, yes. Therefore I can write that Tf is equal to T initial into 1 plus alpha delta theta, power has to be 1 by 2. Again what we said is by using binomial expansion 1 plus x whole power n, that is approximately equal to 1 plus x whole power n is approximately equal to 1 plus nx. So by using that idea we can get that Tf is equal to T initial into S 1 plus, this is like your x term, so 1 plus 1 by 2 into S alpha into theta. So just to multiply and take it here, so I can say that this has to be T final, and inside that T initial into T initial. This T initial is taken this side, T initial will be there. So that is equal to T initial into 1 by 2 alpha into delta theta. This is called a change in time period, yes. So therefore I can say that the change in time period is given by delta T. So delta T, that is equal to Ti into 1 by 2 alpha into delta theta. So take this one down, then we can write that delta T by T initial. This is called a fractional change in as a time period of the system or pendulum. So that is equal to 1 by 2 alpha into delta theta. So this is the important results. If this pendulum is used for measuring the time, that is called a pendulum clock, we can see that. So in that cases, the fractional change in time, this is time period, fractional change in time period, and this is fractional change in time. So fractional is change in is time. Suppose this pendulum is used to measure the time, yes, then delta t divided by t, that is equal to the same thing 1 by 2 alpha into delta theta. Or we can say that from this, so delta t that is equal to 1 by 2 alpha into delta theta into t. So this is the important expression to calculate whether the system or the pendulum gains the time or lose the time during the temperature changes. So how to find out that one? Means you just take this expression here. Therefore I can say that, yes, I can say that delta t that is equal to 1 by 2 is alpha t into delta theta. This is time, so please be careful with that symbols. So you just see this situation. So in this case, for example, delta theta is nothing but theta final minus theta initial. If delta theta is greater than 0, that means theta final is greater than theta initial. That means when temperature, that is when temperature increases, time period also increases because L increases. When time period increases, the time measured by the clock will be decreases. That means there is a loss of time. So it shows the less as time, so loss of time. And similarly here also, delta theta is less than 0. That means theta final is less than theta initial. Or we can say that when temperature decreases, time period also will decreases because length will be reduced. So therefore time measured by the clock will be increases. That is called gain of time. That is called gain of time. So this is very important. And this t is nothing but given time. That may be 1 day or 1 week or 1 year, something like that. They will give that time. Yes. So the next one is fifth is application. So fifth application is measuring scale or measuring scale. The effect of thermal expansion on measuring scales. So let us consider the expression for that one is true value or true reading, that is equal to scale reading into 1 plus alpha into delta theta. So this is the formula for scale readings when temperature changes. True value or true reading, that is equal to scale reading into 1 plus alpha into delta theta. Again here we can say that there are 3 possible situations there. So therefore, so true reading that is equal to, so yes, that is not visible, so we can write here. So true reading that is equal to scale reading into 1 plus alpha into delta theta. So just take the 3 cases here. Since this term depends on this delta theta. If delta theta is greater than 0, that means final temperature is greater than initial temperature. That means when temperature increases, this term is in positive. Yes, therefore in scale reading something is added. Therefore we can say that true reading is greater than the scale reading. In this case, when temperature increases, that is when temperature increases, the true reading is greater than the scale reading. Okay. Now you please see that another one is delta theta equal to 0. So therefore true reading is equal to scale reading. There is no problem with this. And next one is delta theta has to be less than 0. So in this case we can say that theta final is less than theta initial. So that is temperature decreases. So when temperature decreases, the divisions between the successive divisions, gap between the successive divisions gets reduced. So because of that, we can say that the true reading is lesser than the scale reading. That means in scale it shows the more value when compared to the original value of the material taken for the measurement. So